Okay, this is interesting. Looks like instructions in assignment 7 are different depending on the language. If that's ever the case, as it happened in the first exam, and it may happen again, you will always get full points for answering any of the questions correctly. I mean, in the end, that's our mistake. So yeah, definitely, I will talk to the course responsible to change the instructions to match this here. Now, for the last tutorial of this course, I'm about to shed 2 tears. We're talking about one of the things that surprised me the most, because in the south of Spain, in the south of Europe, particularly in Spain, where I come from, sequences and successions and series are the first thing to be taught in every course of analysis, which actually explains what happened in tutorial number 2 when we were talking about, I don't remember exactly what, but I wanted to give you an argument based on sequences, and I couldn't because it was the last topic anyway. This happens a lot of times. There are many ways to introduce the same subject, and we have a succession. No, divided by n. And we have to answer questions about it. When you're facing a succession, yeah, it's generally called sequence, but you will hear me constantly referring to it as succession, because in Spanish this thing is called sucesión. So yeah, just so you know, these two words actually mean the exact same. So to avoid confusion here. First question, is it bounded? Well, this is obviously equal to 4. This limit is 4. As this thing goes to infinity, this is either 1 or minus 1. So this fraction here tends to 0. And the 4 is there. So 4. So our succession is bounded. Now, is it bounded above or below? So let's see. Let's take any element. For example, a sub 1 is 4 minus 1 over 1. So it's 4 plus 1, 5, which is greater than 4. Let's take another one and see what happens. So our first example seems to oscillate, right? It looks like odd terms are greater than this. Even terms are greater than that. So 4 is not the bound. 4 is obviously not the boundary. So let's see. We examine the odd terms. And the even terms. This is what is called a subsequence or subsuccession. We know that all odd terms are greater than 4. What we are wondering now is what happens with this subsuccession if it's bounded. In order to see that, we know that it will eventually go to 4. We know that a sub 1 is greater than 4. It's actually 5. So what happens with other terms? If we take an element a 2k plus 3, I mean the next element of this subsequence, this is 4 minus 1, 2k plus 3 over 2k plus 3. Now, the numerators are the exact same because the exponent has the same parity. However, 2k plus 3 is bigger. So this fraction is smaller overall. So when we make the difference with the fraction that is smaller, am I doing this correctly? Yeah. I'm going to rewrite this a little bit. This fraction is smaller, it's adding up. So we have that a 2k plus 3 is smaller than a 2k plus 1, which means the odd subsuccession is decreasing. Which means it's bounded by its maximum. Which is 5. Which is a sub 1. So it's bounded above by 5. Now we have to perform a similar analysis on the even terms. And we notice something, and is that minus 1 in power even is plus 1. Sorry, 2k. And from here, immediately we notice that a 2k plus 2 is greater than a 2k. Because this fraction is smaller, but they have minus the fraction. So all this thing is like adding something up. And so the even succession, subsuccession, is bounded by its minimum. It's bounded below by its minimum and above by 4. So in this case, the minimum would be a sub 2, which is 4 minus 1 half. So this succession is bounded above by 5 and below by 7 halves. B, is it positive or negative? It's positive. When 2k plus 2 have the smaller values, it has the bigger denominator. It has the bigger denominator, but the fraction, so the fraction is smaller, But this minus sign here makes it that 4 minus this will be bigger than this, because the thing you are subtracting is smaller. The devil is in the details. No, please don't blame yourself. Analysis of sequences looks simple, but it's not. And then it is, and then it's not. And then you find a succession with terms this big, and you really don't know what to do. But that happens sometimes. Anyway, is the sequence increasing, decreasing, or alternating? Well, we know that the odd terms are all greater than 4, and the even terms are all smaller than 4. So this function, if you pick the first term, you are above 4. You pick the second term, you go below. You pick the third term, you go above. You pick the fourth term, you go below. So the sequence is alternating. However, this subsequence is decreasing, and this subsequence is increasing, as we have seen in part A. And the convergence this we have already done in part A, but the limit of this is 4, which is finite. So n is convergent. Alternatively, you can read this as it converges. Any of the two phrasings is good. Overall, I like converges more than is convergent because it's shorter, but that's already up to you. Now let's do another one of this. Just in case. So we're going to answer the same questions in the same order because they are important. Now, we wonder if this thing is bounded. So if it's bounded, it may be bounded by either its greatest term, its smallest term, or the last term. So first of all, we can take this thing to the last term. We notice that this is infinite. So the succession is definitely not bounded above. What happens below? This is linear, this is a hyperbola. When we go below, we may find the same problem, right? What's the minimum value of this function? Well, if we pick a sub 1, is 1 minus 1 over 1, so it's 0. A sub 2 is 2 minus 1 half, which is 3 halves. A sub 3 this thing right here. Now I have to I have to do a poll with you guys, and that is, do we accept a sub 0 or not, and why? The answer is absolutely no. Like, let's see what would happen. A hypothetical a sub 0 would be 0 minus 1 over 0, which is something like this, so it would not be bounded. However, we notice that a n plus 1 is greater than a n. How do we do that? Well, we pick this thing. Right, so this thing cancels here. And for this thing, we already have it, right? This is greater than n, and this is greater than n minus 1 over n. Exactly, we cannot divide by 0. We notice this thing. So our succession is increasing. So if it's increasing, bounded up and not bounded above, it means it's bounded by its first term. That's a1 and that's 0. Which makes sense because all these terms are positive. Except for the first one. Now, so increasing, decreasing, or alternating, we have already answered. Each of these terms is greater than 0, so the succession is positive, and convergent, divergent, or for A, and A does not converge. And that will be it. Okay, so I'm going to continue with a very fun one. As you see, there is some similarities with analysis of functions, but we have the additional difficulty that we cannot derivate because successions are not continuous. So let's go with number 7. Number 7 reads, now, this thing is here to scare us. Let's rewrite this in a nicer form. Now it's less scary, right? This halves in the exponent means we take the exponent of the root. And so by properties of powers, we have that E over square root of pi in power n, which I'm going to write like this because it's interesting. If you look at it, the square root of pi is somewhere between 1 and 2. So E over the square root of pi is over E halves is between E halves and E. This is, sorry, the sign is going the other side way. And here, this thing is greater than 1. So what I want to explain you here is that the basis is greater than 1. And what's going to happen is that you take the limit of this. It's obviously infinite because the exponent is greater than 1. It just goes all the way. Second of all, the sequence is positive. If it's bounded, it's bounded by the lowest term because an plus 1 is equal to E over square root of pi a sub n, which is greater than a sub n. So the sequence is increasing. So the lower bound would be the first term, which is E over square root of pi. And finally, is the succession convergent? No, sir. And this will be it. Okay. So I'm giving you one more. So as you can see, analyzing sequences is extremely similar to analyzing functions, but since they are discrete, well, there are several tools that we need. Comparisons, we have to deal with inequalities, and sometimes that doesn't grind up very well. But there is really not much more to it. However, let's take another example. And the first thing I'm going to make you notice here is that that thing happens. A1 is equal to 2, A2 is equal to 1, and A3 is 2/3 in power cube. So really, the interesting part of this sequence begins in A3. So let's see what happens here. First of all, is it bounded? What happens in the end? What happens in the limit? The limit when n tends to infinity of an is 0. Why? Do you remember that on the second tutorial I mentioned something like that? which means nothing grows faster than n over n over time. So if you have something here that tends to infinity, something here that tends to infinity, but the thing that is in the denominator is much larger. And I mean, so much larger, what is on the other side is absolutely insignificant. So the limit of this thing is 0. Now let's see what happens. We know that A1 is 2, A2 is 1, and AN is smaller than 1 if n is greater than 2. The reason why is this. A power of a number that is smaller than, the power of a basis that is smaller than 1 is between 0 and 1. That number is also between 0 and 1. So really, upper bound would be 2. And lower bound would be 0. Why? Because this thing is decreasing. How do we see that? Let's take an plus 1. An plus 1 is 2 in power n plus 1 times n plus 1, which is 2 over n plus 1 times 2 over n plus 1 in times n. This is smaller than n greater than 1. N greater than 2. If we have n equal 1 and 2, we have the comparisons here. And so this thing is smaller than 1. So this is smaller than 2 over n plus 1 over n, which is smaller than 2 over n in power n, since 2 over n plus 1 is smaller than 2 over n. So yeah, our sequence is decreasing, is uniformly decreasing to be exact. And so for the lower bound, the limit now it's decreasing. Is it increasing? Obviously not. Is it alternating? Obviously not. Is it convergent? It is convergent. It converges to 0. And that's all we need about this sequence. Now I'm going to move into infinite series, which are sums of sequence. So let's take 5 minutes. Let's be back here at 1/4, and we will move on. Stay hydrated. There we go. We have another geometric series. What's the sum of this? This is finite. This thing in absolute value is smaller than 1. So this converges to this thing right here over 1 minus 2 over e. Let's see if we can write this a little bit better. This is at cubed. This is e minus 2. And this is divided by e, so this thing goes up. And this is 8a4 over e minus 2. Okay, it doesn't look much better at all, so you can just choose it. But this is the case. This is more or less how it works. All right. So moving on. Most of the series that exists, we don't know how to sum them. However, one thing we know is how to determine if the sum is finite or not. We have that thing there, and we have a criterion to determine convergence, which is called the Quotient Criterion, or something like that. And it says that if the limit when n tends to infinity of a n plus 1 over a n equals 0, then the series converges. If I remember correctly. Sorry, between zero and 1. That's it. So let's see what happens. So the idea is that as a sequence, a sequence that shrinks in difference, that is bounded, actually has some, I'm going to call this rho, as they do in the book. And so rho, in our case, is the limit when n tends to infinity of an plus 1 over this thing. It had to be smaller than 1, right? Smaller than 1. Now, this is the limit when n tends to infinity and as you may have heard me said a million of times, this limit is 1. So no info. However, there is another way to determine whether it converges. So let's use it. I mean, we don't have really a way to know if this thing converges using tests. This is also called ratio test, by the way. In order to determine if this series converges or not, I'm going to require an additional result. Which is this thing here. Now, this is, let's call this an, let's call this bn. And one thing we're going to notice is that AN since both series are positive, because all terms are positive, AN being smaller than BN for all n, it means that the sum is also smaller. And this obviously is greater than 0 because all terms are positive. So yeah, the series converges. The series converges. Can we sum this series? I don't know. I really don't know. If it was n squared minus 1, it will definitely be possible, because then it will probably become telescopic or something like that. But this one, I actually have no idea what the sum is. Now, let's call this thing AN. And I'm going to make you recall a very old result. If you have two numbers like this, then that thing is true. Why is this important? You may think it like this, okay? As an example. Why is this important? You might be asking. Because this thing being true means boom, explosion. Okay, there are two intermediate steps, so I'm going to go out of my way to explain this. And let's call this sum S. If we take out the term in 0, the term in 0 is 1, and so we have the term, from 1 of n squared plus 1 over n cubed plus 1. Using this inequality here, this is greater than 1 plus the sum from 1 to infinity of n squared over n cubed, right? Because n cubed is greater than n squared for every natural n except 1. But anyway. Sorry. But this thing is called the harmonic series. And if we have a series from which we know that the sum is greater than the infinity itself, does it converge? No, sir. It doesn't. Now, an interesting question about this thing is how many aces do I have up my sleeve? And I'm going to answer you with many, actually. So let's take up number 19 and see what happens with it. Number 19. I think it starts in 0. No, it starts in 1. Right. Now, what do we do with that one? Here we have a factorial that grows super fast. And here we have n squared, which doesn't grow too fast, but in power n does. So first thing I'm going to try and do is a ratio test. Let's see what happens. Let's call rho the limit when n tends to infinity, an plus 1 over an. Here we have n factorial, sorry, n plus 1 factorial over n plus 1 squared in power n plus 1. And down here we have n factorial n squared in power n. You may get surprised with this one. So that quotient is no other than n plus 1. And now this thing becomes the denominator, this thing becomes the numerator, and 2 in power n n plus 1 squared in power n plus 1. Right? Correct. So this thing cancels here, and this thing cancels here. And so what we have is the limit when n tends to infinity of n squared over n plus 1 e. And this definitely shouldn't be the case. Let's see if I have done something wrong. I may have done something wrong here. Let's not rush it. So no, I was right. we obviously have a problem here. I mean, this is kind of telling me that the factorial grows much faster than n squared in power n. Which looks definitely like the case. The ratio test, if I remember correctly, is a necessary condition. So each term being on the infinite many times greater than the previous one means that there is absolutely no way this series can converge. Like, yeah, in the infinite, its term is much greater than the previous one. And so that's number 19 for you guys. As for number 35, we wonder if that series converges. We already know that it converges. And we also know that its sum is somewhere between 0 and pi squared over 6. But we are asked to use an integral test. So what we are going to do here is assume that each term is a function evaluated in n, and so this sum is finite if and only if this integral is finite. Let's see what happens here. This is so, yeah, the integral converges, so the sum converges. Again, do we know what the sum is? I don't think so, but we know that it's finite. Now, let's see. So yeah, for those of you who may be wondering, the idea of the integral test is doing an integral instead of a finite sum, instead of an infinite sum, and the convergence of or divergence of both is linked, so they are equivalent. So you can always treat your sum as an integral and see what happens. You will not get to the sum. I mean, they don't have the same sum, but still, you can determine whether or not convergence is there. Now, for number 39, we're using the root test. So I'm going to rewrite this a little bit. just in case. And so for our root test, we have L, which is the limit when n tends to infinity of the nth square root of the nth root of a sub n. So in our case, which is no other than that. Is it possible to turn the sequences into functions and then just write an improper integral to find whether they are convergent or divergent? That's exactly the integral test. You turn your infinite sum into an integral, and if the integral is finite, then the sum is finite as well. Now this is an indetermination of the form 1 over infinity, and that kind of rings a bell. That kind of rings a bell. Okay, this is an indetermination we have never seen, and it's 1 in power infinite. This is something like that. I don't remember the exact exponent now, but when you find what we know, actually number e is defined as this limit. So this is definitely a negative power of e. Actually, another thing we know, it's like that, if I remember correctly. So yeah, this is some power of it, some negative power of it, to be precise. So this is smaller than 1. Can we try a series when we try the integral test? You just missed one. We just did number 19. No, sorry, we just did number 35, I think. But we can do it again. So now let's see the root test. The idea here is that this limit is smaller than 1. In the end, it's a base. It has a basis that is smaller than 1 in power infinite, so it's some negative power of e. By the root test, we know that S converges. Can we rewrite as x over x plus 1 in power of x? I don't know why you would like to do that. But yeah. Don't remember the exact number now, but stick to E in power something. So the conclusion of this exercise is that this sum converges. So this was the last of the recommended exercises. X over x plus k plus 1 is in power minus k. Yeah, definitely. Sounds good to me. Okay. So we have 15 minutes left. So I'm going to try and do one of these random integrals with the integral test and see what happens. I don't want to give you a too complicated example because there is a chance that we actually never know. In this case, this is 2 plus n minus 1. So we can put it in that form. If we were to run an integral test, we put this as an integral with these limits, 0 to infinity, of the terms. Like that. And so this thing is the limit when n capital tends to infinity of the proper integral, and this is something like that. Needless to say, this is infinite. What does this integral being infinite tells us? It tells us that the sum is infinite, and so the series converges. The series diverges, sorry. Now, you may be thinking, this is n minus n when n tends to infinity. Why is this limit infinite? The reason why is because n grows linearly and the logarithm is much smaller. That thing right there. So yeah, the series diverges. However, that's something we should have been able to see from the very beginning. We can run another tests. However, this thing here is somewhere over there. So in the end, each time we advance a term, the withdrawing power of the 1/2 plus n is smaller and smaller and smaller, and so the ones end up dominating here. In any case, this was the integral test for you guys. I'm going to run a ratio test as well and see what happens. Anybody seeing something interesting in this limit? It's equal to 1. What does it mean? The ratio test is inconclusive. If you run the root test, actually you will find a 1 as well. So yeah, there is really not much about this series unless you either run into this idea or you run into the integral test. So it's very good to have it. It's really good to have it. How should we know which test to run? Generally, if you have something in power n, you can run a root test. If you have a quotient of polynomials, you can run a ratio test first. And if you have any other types or things that you know how to integrate, you may run an integral test. But beforehand, there is a necessary test that we haven't done. And that is the limit when n tends to infinity of a sub n. If this thing is not zero, the series will never converge. So this is the first test that you have to run. I just don't remember the name now. But the limit of this thing, the limit of a sub n is 1. So this thing will never converge. So yeah, the order to run tests, this thing is first, all the other tests are second. Because if this test fails, then we can't have convergence. If this test doesn't fail, and by this I mean this limit is 0, we may have convergence. And then we have to run other tests, or maybe squeeze the sum between 0 and some sum that we already know, or something like that. But first, this thing always. And guys, with this, I think I'm going to call this a day, because it's 12. We have run a lot of exercises. You already have a lot of things to reflect about.